Okay, good afternoon. Welcome to Lecture 30. Today we're going to continue talking about methods or things you need to know in order to do inspection analysis. Today we're going to be doing the terminal gains, so the gains from one terminal of the transistor to another. As usual, a few announcements before I start. First, homework number 9, you know, is due this coming Friday. What's going on? Okay, somehow this is not seeing the screen, so I'm going to unplug and plug in again. There it is. Okay, so yeah, homework 9 is online. Lab 5 is due this coming Tuesday. I put something up on the website to give you a little more help on what you should do for your report for that lab. It's all the obvious stuff. I was going to leave it freewheeling for you to create a report, but I think it's better to actually have something where you can specify exactly what goes on to that report. Why don't I talk about that a little bit? Okay, so as you know, you have a report that you have to turn in. Unfortunately, I've turned off my touch screen, so I've got to do it this way here. But it should be concise. I don't know if 10 pages means concise to you, but try to fit it in that 10 pages there. And so what it should have in it, okay, looks like I have to go down the sides here. Format, you should have the following sections here, right? You should have design strategy and discussion, an explanation of your hand design and some of the details of that, computer and SPICE simulations, experimental results, and a summary, especially with a table there that summarizes all of your different results. You should have a column with all the specs that we gave you, what your hand analysis says you should have gotten, what SPICE says you should have gotten, and then what you actually measured for that. And all of this should be backed up by written prose that specifies things like how did you approach your design, what were the trade-offs, if you had to iterate, describe how you guided your iterations, and this hopefully this says something about the voltage across the resistor RC, that sort of thing, because that seems to dictate almost everything about this design here. Use equations like that to help explain this. You should have a clear diagram showing your circuit topology and a table summarizing your complete design even before the summary table. So this is a table that should show your operating point, all the different currents, all the different voltages, maybe what the GM is and that sort of thing, those details there. And then you should have a summary section that I already mentioned, should have a table that compares all those parameters that you were designing for. Compare the results, explain the discrepancies between your hand analysis, SPICE, and your experimental measurement. I guess needless to say, show all your work in this, show the calculations here, but don't show everything that led up to your final design. Just show your final design in the end. Don't show all of your iterations for that. And then, of course, you're going to need some computer outputs and plots on this. And it'd be nice if you put those in a nice, so if you don't know how to do this, you're going to need to learn how to do this. But in Word or whatever you're using to make these reports, you know, create a little figure area with a figure caption under that for all of your plots and that sort of thing. Okay, so this should look somewhat professional, I suppose. As professional as you can make it, I suppose. Okay? So that's sort of a summary of what your report should have in it, just to give you a little bit of guidance on that report. Remember, this is worth a good amount of the labs here, so you want to do a good job on this. Just remember, what's graded is your report, not necessarily what you did in the lab, which is an unfortunate thing, of course, but that's life. So make sure your report looks good. Don't be iterating to get your design all the way up till Monday night, and then only have one night to put your report together. Make sure you put enough time in there so you can get your report done. And since we extended the deadline, hopefully you do have that enough time, but as we all know, things always creep up towards the end. Okay, some other, yes?
Are reports with partners, or are they individual?
No, they're individual, actually. So we'd like to see an individual report from everyone. So, of course, your design is with a partner, and so some of the things in your report will be exactly the same. But we'd like to see an individual presentation from all of you. Yes?
So is the report just 100% of that 5, or is it broken down into our circuit and the report, or how does that work?
It's 100% of Lab 5, so, right? Because the experimental section represents what you did when you put everything together. I think someone on Piazza asked whether or not you should take a photo of your board. That'd be cool. I would, just to put that in there. But the more important thing will be your circuit diagram with values of the resistors and capacitors that you were using in that. Because your TAs, when they grade this, you know, they'll have seen so many designs, they'll know immediately whether your design is going to make it or not just by what resistors you have in there. And then see what you're, you know. And if you don't make it, you're not dead. You just explain why. If you can have a good explanation why, and they see that you understand all the different trade-offs in this thing, you're probably still going to be fine. Okay? Now, one thing I do want to say about lab number 5, and that in office hours at least, I'm seeing a lot of people, and this is good strategy in general, to save yourself time. I'm seeing a lot of people do the design using an Excel spreadsheet where you put in the equations into that spreadsheet, you let that spreadsheet calculate everything for you, or use MATLAB or something. Don't do that. At least not in the beginning. And the reason why I'm saying don't do that, yes, it'll save you time, but you get good at this by spending time on it, especially for things like the midterm. If you're doing only this Excel sheet thing, you're going to die on the midterm. Okay, so make sure that you are actually writing out the equations, actually plugging in numbers yourself, rather than letting Excel do that for you. At least several rounds of iteration. I would say at least 3 iterations you should do this, so that you get those equations in your head. You understand what the trade-offs are, because when you blindly use Excel on that sort of thing, you don't understand the trade-offs. And this midterm is going to be all about whether you understand trade-offs and that sort. Not all about that, but there'll be some of that in it. Okay? So just a warning to you, yes, it's a great way to do it, but only after 3 iterations, I would say at least. Okay? All right, so speaking of your midterm, that's coming up. So this coming Friday, I'll have an information sheet on the midterm and no past exams or that sort of thing. But you kind of know what my exams look like anyway right now. And I would say that your current homework is going to be a lot like the midterm. Okay? So if you enjoy this stuff where you have to get the input-output resistance, the gain, frequency responses, that sort of thing, I guarantee you I'm asking you that sort of thing on the midterm. Right? Because that pretty much encapsulates the things that you need to understand. Okay, so do this homework. At this point, maybe you can't do it by inspection. If you can, that's great, but it's probably better if you don't. You write out your hybrid pi model so you can see everything that happens with your hybrid pi models. But eventually, for the midterm, you're probably going to want to do some inspection on that, because this is going to be a time sort of thing again. Right? The 2 midterms are time constrained. The final exam won't be as time constrained. But you want to be able to do things quickly. And if you can do inspection analysis, you're much quicker. Okay? Any questions about anything? All right. So last time we were talking about the generally loaded transistor. We talked about terminal resistances. Today we're going to talk about the gains. And once we get that, we've got everything we need for inspection. And so what I'll do is I'll show you an inspection analysis sheet that I'll put up on the web for you. That sort of summarizes all the equations you really need to know and the things you need to understand in order to do this inspection analysis. So let's get with this. So this was what we were looking at, our generally loaded transistor. We got all the resistances seen looking into the terminals, while the other terminals are loaded with other resistors. Okay? And in general, these other resistors can be large resistors, large signal resistors, or small signal resistors. So this RC, R capital C, could actually be a small signal resistance too, coming from another transistor. If I put another transistor up here, that would be the resistance that I see there. So this is a very general technique that I'm showing you right now. We got all of these equations, and I'm not going to go through that again. I'm just going to sort of run through it. The RE equation looking up is R pi plus RB, where RB is hanging off the base, divided by beta plus 1. Okay? So what that tells you is that if I'm looking up the emitter, it makes any resistance on the base look smaller, because I'm dividing that by beta plus 1. Okay? Continuing with this, we also derive then the resistance looking into the base, with the collector and the emitter having loads on them. And so that resistor looking into the base basically was equal to the R pi resistance that I see looking through that transistor, but then the RE in this case gets amplified. So looking up the emitter, it reduces the resistance you see looking out. Looking into the base, it amplifies that emitter resistor by beta plus 1. Right? So suddenly your resistance gets a lot bigger looking into this base. Okay? And that's a trick that we will use later on and that people use in design to increase the input resistance of your amplifier to get something more op-amp-like. Right? Remember, op-amps and most voltage amplifiers like huge input resistances. What a great way to do it right here. Okay? We went through that and derived that same equation several different ways. T-model, hybrid pi model, following the currents and that sort of thing. I'll go through your notes to see exactly how we did that. But then we moved on to get the collector resistance, so looking into the collector. And that resistance, we ended up with a pretty complicated equation here. R naught times all of this stuff. And so it has some dependence on RB. It's got a strong dependence on RE. And so that strong dependence of RE is right here. This is assuming R pi is much greater than RB. But if RB is a large resistor, then you got to use this equation to the left here. Okay, that's a pretty complicated equation. I will ask you to memorize that, but if you forget that, it most likely won't matter, because in most circuits, if you have an RC resistor hanging off of this, that RC resistor cannot be gigantic, and so it's probably going to be a lot smaller than this RC, which is now going to be gigantic because it's that original R naught times something that's greater than 1. Okay, so in the end, this whole thing will just boil down to that RC. And last time I forgot to put the line down that final C. It's there now. That's the C that I meant for that. Okay, and so just some remarks about this. And so here's the new stuff coming in, but I just wrote up some remarks on that final one. So that RC, it's always good. You know, in lecture I'm trying to go quickly so I can finish all this stuff, but it's always good for you when you're doing your homework or even after lectures, plug in some numbers to figure out the order of magnitude size of things. And so it's a good thing to do with this R little c here. So R little c is going to be this 1 plus GM times RE times R naught. So if I do that, 1 plus a typical GM is like 0.04, that's for 1 milliamp, times the typical RE is 1 kiloohm or so. And if I do that, if my R naught was 100 kiloohms, that makes RC 4.1 megaohms. That is a huge resistor compared to the generic RC resistance there. But it is not huge compared to other transistor resistances. So for example, say I had this, okay, which is a typical type of transistor configuration you're going to see. And so I'm already talking about things that I haven't taught you yet, but already you should be able to analyze this just with what I've told you. Because if you look at this, I'm taking this transistor Q1, so think of this as where the input signal is coming in. And I'm loading that instead of with an RC resistor, with another transistor. Except this one's a PNP device. So it's a PNP device, so that means my collector is below the emitter when I'm drawing this thing. And they're both sort of exactly the same. I got an RE1 and an RE2 on that. That means the resistance I see looking into the collector of Q1 is going to be this R naught times 1 plus GM RE1. If I have numbers like these above, that's 4 megaohms. Same thing for the top. If I choose similar numbers for RE2 and for the GM through Q2, I'm also going to have 4 megaohms looking up. And so in this case, I cannot ignore these resistors because they're both the same size. And the total resistance I see looking into this node here is going to be the parallel combination of these two resistors, which is 2 megaohms. Okay? And so that's how we'll do our analyses here. We'll remember what that resistance is. And we'll be able just to look at the transistors and just say what the resistance, just write it down immediately without having to draw out a hybrid pi model. Okay? So here you can already see some of the power of this. Now, if you don't have these equations in your head, then it may look like I'm doing magic right now. But believe me, just a little bit of memorization, and it's not a lot, and you're going to be able to do the same kind of magic. Very quickly be able to say what these resistances are. Okay? But that's resistance, and so that's not enough of the picture, we need to also get the gains in order to be able to do a full analysis here. Okay, we need those resistances mainly because we need to take into account loading for the gains. But let's now go through and get gains. And so we got the gain for a common emitter amplifier. What I'm talking about now is getting a gain for this generally loaded transistor that now has resistors around it. The emitter is not going to ground. It's going to ground through a resistor. So let's do that. Let's get what I'll first call base to collector gain. Okay, so for this, I mean I'm attacking this circuit where I have this RC. I have my transistor. Then I have an emitter resistor down there too. This is going to be my output there. And this is going to be my input. And so this is what I'm going to worry about. Let me call these VB and VC, actually, for this whole thing. Okay, so I want to get the gain of this. And I guess I can assume that, you know, somewhere here I had an RB resistor, but I don't care about it because I got the gain already up to this node here. And so all I'm interested in doing now is getting the gain from this node to the output node of this thing. And so how do I go about getting this? I already know the resistance that I see loading this thing here. I already know that I have an Rn here. And can you tell me what that resistance is? No, you can't yet. Next time I ask this, I would like you to be able to tell me immediately what it is, because you'll have this memorized. That's just R pi plus beta plus 1 times Re. Okay? Can you tell me what this resistance is? That's the R naught that I want. Yeah, that's a little R naught, but it's times all that other junk, right? And so if I have all that other junk, then that's going to be, you know, a whole bunch of junk. But you have to have this in your head, and I have it in my head. So that's 1 plus that RB over R pi on that times that R naught. Okay, in parallel with RC. Right? So that's what that resistance is, but that's pretty much about equal to RC. So just by inspection immediately, because I have those equations in my head, I just wrote that. I didn't draw a single hybrid pi model. Okay? But what we don't know is this gain. I want that gain. Okay? And so the way that I want to get that gain, and the general way to think about gain for these things, and I guess this is a general, I'm calling it a general way, but it actually is something, it's a specific way that we're doing it now. And the specific way that we're doing it is that we want to create a network out of this. Right, we already have the input resistance and the output resistance. And so what I want to do is convert this transistor loaded with resistors to an equivalent transistor. So convert to an equivalent transistor Y parameter model. So it's going to be just like the hybrid pi model. So I'm going to draw it like this, except this resistance looking in is going to be Ri. Instead of R pi, that's the Ri, and that's the Ri that I just wrote on the left side there, that I got by inspection, but that you can get by putting the hybrid pi model in if you want to waste your time. Okay? But just off the bat, I know what that Ri is. But then I want to have a controlled current source here. And I want this controlled current source to be, if I call this little VB now, which is what that ends up being, and I'm effectively going to make this grounded. So I'm removing that RE resistor and turning this into a transistor that looks like it's going to ground, but it's not the same transistor. It's a transistor that absorbs everything. So I'm drawing that for everything in this box here. Okay? And so this is now, I'm going to call a capital GM. Because that's everything in the box, it's no longer a lowercase gm, I'm going to call it a capital GM. And this is what most people do conventionally. So that's capital GM times my VB there. And this now is going to go through a resistor here, and that's going to be a capital R naught. Okay, so this effectively is what I have. I've just Right, so this is my VC, that's my VB terminals there. This is basically, I want to equate this circuit that includes transistors and resistors to this, which is like a, quote, new transistor. It's got a different R pi, it's got a different little R naught, it's got a different GM in this case. I know the RI, I know the R naught already, I just wrote them down for you here. Okay. What I want now is the GM, the capital GM. So all we need now is capital GM, which by definition we call the short circuit transconductance. And that short circuit transconductance, GM, equation-wise, is equal to IC over that VB that I have with my collector shorted. Okay? And so, again, I'm looking for this GM there. And so let's go ahead and do that. And let me cheat a little bit like I've been doing, which is grabbing this circuit. So in order to get that, I need to do an analysis now. I want to get this capital GM is equal to IC over VB with VC equal to 0. And so VB equal to 0, or VC equal to 0, to me means I'm going to short my output. Right? That sets VC equal to 0. And thus my short circuit transconductance I'm getting, where transconductance is equal to a current divided by a voltage, right? Just like a conductance is. And so what I'm going to do is an analysis on this, but I have to treat this with the original circuit, so I can't just do that. I guess I'm going to have an RC here, which isn't going to matter because that's been shorted out, right? So this thing, I'm drawing it there just to be complete, but it's not really there because I just shorted my output. My emitter has this emitter resistor, and I'm basically making the equivalent circuit for the original device that I'm analyzing, which is this one right here. Okay? And so the input here, I'm just going to drive with VB because I just want to satisfy the definition of this capital GM. I have to drive with VB, I have to measure the IC that results when the collector is shorted. Okay, so this is a circuit that I'm analyzing here. So let's go ahead and do this analysis. So the first thing I'm going to do is what we usually do. I'm going to neglect R naught because it's very large, I'm assuming, versus all the resistors that I have in this circuit. And then I'm just going to start my analysis. So the first thing that I can do, for example, can define a voltage across RE, call that VE, and I can write that voltage here. That's going to be all the currents going into RE times RE. So all the currents going into RE are, first this current going through R pi, which you can see since it has VBE across it, is just VBE over R pi. Then I've got this current GM VBE, and that whole thing times RE. I can factor out my VBEs from this and write VBE times quantity 1 over R pi plus GM, that whole thing times RE. Okay? But what I'm really interested in here is VB, and VB, right, because I want to plug VB into this equation to the left here. GM. I want to get an equation for IC, and then I want to get an equation for VB, and then take the ratio of those. So by equation for VB, you can see from this with KVL across that, that gives me VB is just going to be equal to my VBE plus my VE. I have equations for these already. So I have VBE times 1 plus this quantity, 1 over R pi plus GM times RE. Okay, I know what IC is equal to. IC is just being equal to GM times VBE, right? Because that's going straight through a short to VC equals 0 there. I shorted the output there. And so now I could take these two and write out an expression for my capital GM, which again is IC over VB with VC equal to 0. I'm just going to take the ratio of these, GM times VBE divided by all this stuff here, VBE times 1 plus 1 over R pi plus GM times RE. I can see that I'm going to get some cancellations there. And so VBE's cancel right there. I can also say that this GM here, now maybe I can fit it all here. So in this thing here, GM, I mean R pi is equal to beta over GM, right? So 1 over R pi is GM over beta, which means 1 over R pi is much less than GM, right? So that means I can neglect this 1 over R pi versus all of that, and in the end, I end up with GM being equal to GM, little gm, over 1 plus little gm times RE, and that then is my equation for capital GM. Okay? So what I've done is I've defined a new GM for my amplifier, and that means I can write my gain very quickly for my amplifier, the gain in the end, which would be VC over the VB that I had in the original amplifier picture. That's just going to be from just this circuit here. That gain is just equal to minus GM times that R naught. So whatever is hanging off of my collector, that's the R naught. That's the capital R naught, whatever's in shunt with the collector. And I'm just going to multiply it by capital GM, which in this case is that lowercase gm divided by 1 plus lowercase gm RE. Okay, all coming from this. And so I did that fairly quickly. You may have to go through again and look at those notes to see how I derived all of that. But this is what I'm going to remember here. I'm going to remember that this is my gain. And from my gain equation, the other thing I have to remember, and this is an easy equation to remember here, right? You know that that's, that the gain is always a minus a GM times a resistance. But now it's a capital GM, and that capital GM in this case, you just have to remember, is GM over 1 plus GM times RE. Or you can, if you like this form better, GM over 1 plus big RE divided by that little RE, where that little RE is 1 over GM. Okay, so these are the same things. Looks like an E there. But this in the end is my total gain equation that I will use whenever I see a bipolar transistor and I want the gain going from base to collector in this case. Okay? And so this is with general loading. What if RE were 0? If RE were 0, then this would be a common emitter, right? And in that case, this thing reduces to just GM, right? If RE is 0, this reduces this GM, and that gain becomes minus GM times whatever is hanging on my output R naught, which is exactly what we got before for the common emitter. So what I've just derived for you is a generic general equation for capital GM. And your gain is always going to be minus capital GM times R naught. You just figure out what GM is, you just figure out what R naught is. Okay? So if I had to take this amplifier right here and get that gain, and just write down that gain now, I can do that. I could say that VC over VB is just minus that GM times R naught, but I know that that GM here, because I have an emitter resistor at the bottom, is going to be GM over 1 plus GM times RE, and then I'm going to multiply that by all of the resistance I see at this node right here, which is R naught. And all the resistance I see at that node is just whatever I see looking down this way, which is my R little c, which is a complex equation, as you've seen, in parallel with RC. That's it. That's my gain. By instant inspection, by just knowing these equations, I wrote down my gain. Okay? Yes?
That's RC parallel RE?
No, this is a little RC here. So that little RC is that R naught times 1 plus GMRE over 1 plus RB over R pi, that thing. That's the R little c. Okay? It looks like a lot right now, but get practice at this and you'll see you'll be able to do this very quickly. But get these equations in your mind, I think is the first thing that I want to tell you on all of this stuff here. Okay? So that's base to collector gain. We have two other gains to get. Right? Because we have this, I can go from base to collector. I can also go from base to emitter. If I took my output on the emitter, I want that gain. So let's get that now. So for this, what am I talking about? Still generally loaded transistor. Have my RC. I have my transistor there. I have my RE. I'm coming in with a voltage at my base, but now I'm interested in taking my output from the emitter. Okay? Same thing. I haven't seen this before, so I want to analyze this with a small signal circuit that includes my hybrid pi or my T model. And it just so happens it's much easier to see things in this case with the T model. You can derive exactly the same thing with hybrid pi, but I'm just going to show it to you with the T model now. So let's insert the T model. And in this case, the T model, as you'll remember, is this. I have a current source that's alpha times IE. I have a little RE here. And my IE is going through the little RE. Let me make that look like a little RE. There's my IE going through that. My base voltage is right there. This is going up. I do have an R naught resistance here. I have an RC right there. Okay, and then this is now my output terminal. My emitter is my output terminal. And I still have an emitter resistor here, of course, because I'm trying to keep this a general case. So this now becomes a circuit that I have to analyze in order to get my gain. But if I look at this circuit, what do I see here? This region right here, from VB through RE out there, that's just a voltage divider. And that's all that is. And so that means I can immediately write my gain from VB to VE as just being equal to that RE divided by little re plus that RE. Okay? And if my R naught is not that big, okay, but it is still bigger than RC, then I can also write this more correctly as parallel with R naught, because that R naught is essentially going to ground here. If I say that RC is much less than R naught, but R naught is not that big. Okay, so often that's what it's going to be here. So you'll have this in parallel with R naught here if the collector is going straight to ground, or if the collector is going to ground through a small resistor RC. If it's not going to ground through a small resistor RC, then you can't really use this as blatantly as I'm doing it. But you can pretty much, because usually you'll never write that. You'll just write this. Right, because in general, R naught is going to be much greater than RE. Okay? And so if I look at this, what's little RE? Can someone tell me what little RE is? Yes. I mean, it in principle is alpha over GM, but yes. It's basically 1 over GM. So if it's 1 over GM, I can also write this as GM times RE over 1 plus GMRE. So these are all different forms of this. What's the value of little RE? If I had IC as 1 milliamp, what's that value? 25 ohms. Okay, for RE, right, if you have RE that's generally in the kilo ohm range, this is just 1. Okay, so this is why this is often called an emitter follower. It just follows the input. It's like a unity gain buffer is what this ends up being. Okay, but these are the equations. If it's not exactly a gain of 1, if you need it to be more accurate than that 1, then you use these equations to get that gain. But it's very simple stuff. Okay? So that's my base to emitter gain. And so I've got gain from base to collector, base to the emitter. The only other gain that I can really get out of this, unless I want to use this transistor in reverse active, which I don't want to do, right, is to go from emitter to collector. And so that's my final case. I'm going to get emitter to collector gain now. Okay, so emitter to collector gain, it's going to look something like this. The circuit eventually, the small signal circuit, after we've eliminated all those bypass capacitors, etc. In a general sense, this is what our circuit will look like. So I'm hanging off of my collector in RC, hanging off of my base in RB. I have my output voltage VC. In principle, I'll have some resistor here, RE. But I won't care about that because I'll assume that I've absorbed that in the previous stage, right? And going from stage to stage, I absorb the impedance of the next stage, as I showed once, but I'm going to show many more times later on. And so this is the same thing. I want to equate this to that same circuit that we talked about, except now I'm going to have VE across this. That'll be grounded. And I again want to determine what GM I have for that VE. And this will be a capital R naught voltage there. And that's my VC. Okay? So it's going to be the same situation that I want again. I want to get the big GM of this, and I'm going to want to know the input resistance and the output resistance. But these things I already know, right? Do I? What's that input resistance? Looking up an emitter. Yeah, you don't have them in your head yet, but what it's going to be, remember, is it going to make that RB look bigger or smaller when I'm looking up the emitter? Smaller. Excellent. Good. And so now, with that, can you tell me what this is going to be? So I've got basically an R pi from the base to the emitter. And then I've got RB. So it's going to be the sum of those two divided by beta plus 1. Right? Okay, and then I can also go for an R out resistance here. This is just going to be that RC resistance essentially. But I can also say that it's going to be in parallel then with that R naught in 1 plus GM RE over 1 plus RB over R pi. Okay? Now, if I couldn't remember that last one, it wouldn't have mattered because it's so much bigger than R capital C. On an exam, if I ask you for the equation for this resistance, I'm going to want to see that R naught equation. If I ask you just for the number, you can ignore it. Okay? So in your calculation, you'll ignore it. In writing the equation, you'll write this R naught thing. Only in this class, because I just want to make sure you know it. But when you take 140 and the rest, you'll just ignore all that stuff. Okay? And so those are the resistances immediately. I want now to get what I don't know. So again, okay, all we need is this capital GM, which is this similar definition, IC, but now divided by VE, also with VC equal to 0, also still called our short circuit transconductance. Okay, so let's go ahead and get this. And so to do this, I need to draw my hybrid pi model, because I haven't attacked this problem before. Anything you see that's new, you got to attack with your hybrid pi model. At least you should. Brand new stuff. But then again, as soon as we've done it, we're just going to forget about the hybrid pi model and just remember what we got. So I'm going to drive at VE, right? I'm trying to drive with VE and measure my collector current like I was doing before, except I was driving with VB before. And so in this case, what do I see? I see with my hybrid pi model, basically my R pi resistor is right there. That then goes into my emitter, or my base resistance, emitter resistance. No, base resistance. Because the base is coming down. Okay? And then I've got my current-controlled current source, but this now is going to go in this direction here. So that's my GM times VBE. And my VBE is basically in the opposite direction of the way that I have drawn this here, across that R pi. So there's my VBE there. And then from here, I've got my R naught resistance. And I have my collector resistance here. But I'm again going to short this because I want my short circuit current IC. So I want to solve for this, where I'm going to take IC divided by VE with VC equal to 0. And so that's effectively how I'm making VC equal to 0. I'm short circuiting my output. Okay? So let's analyze this thing. Again, I will neglect R naught, because I'll assume that it's much larger than any other resistor across this. And I'll just start writing some expressions for some of the voltages that I see here. So first of all, I've got this VBE voltage. So this VBE is basically generated by VE across this voltage divider that I've got between R pi and RB. Right? Except that voltage is going the opposite direction, so I'll put a negative sign there. And so I'll just write this as VE times R pi over R pi plus RB. Okay? And therefore, I can write an expression for IC immediately. So IC is going to be GM times VBE. If I neglected that R naught there, right, all of that current is just going to come from GM times VBE. And if I plug this into that, this is going to be minus GM times R pi over R pi plus RB, and all of that times VE. And now just rearrange this thing to get my capital GM. Capital GM, which I remind you is IC over VE, with VC equal to 0. This is then just going to be equal to exactly what this is here, but I'll separate my GM from this. That'll be GM times what looks like a voltage divider between R pi and RB. Okay, and this now is my expression for GM, for the gain of this stage here. So my gain is still going to be equal to, right? So I could still write that my gain VC over VE. That's still minus GM times R naught. But notice this GM is negative here. Right? And so if I had the case for this thing, if I had the case where RB equals 0, which is a common case, then capital GM would just be equal to minus GM. The minus sign on this GM cancels with the minus sign outside of this gain equation here. And so if I had to write the gain for the case that we're looking right here, this thing up here, I didn't leave my space to put gain there, but I'll write the gain right here. I'll just say for the initial circuit. The gain from that initial circuit is now then going to be minus well, let me not bother with the minuses because I don't have enough space. The minuses cancel out, and I'm just going to write this as GM times R pi over R pi plus RB, finally times that collector resistor there. Okay? And if RB is equal to 0, the gain simply then is going to be GM times RC, and it's going to be positive gain. Okay? And so this is finally the gain of that circuit that I just drew there. For the two cases, if I have a finite RB and if I have RB equal to 0. Okay? And so these are equations now that you should memorize. You should have in your head. And I derived all of these things fairly quickly, and I don't know how messy I'm being. Actually, that handwriting looks pretty good as far as I can tell right now. That's pretty good. But I've done something better for you, though, to help you with all this, because I really think this is important. If you can master this, you can really become an excellent circuit designer. And so I'm giving you this. This is all of the equations. I mean, it looks like a lot. I claim 6. I claim this is 6. But it depends on what comes natural to you. So what do I mean by what comes natural? When you see a resistor in a circuit, what are you thinking? You're not thinking, oh, okay, this is okay, there's a current source here, there's a GM there, there's an R pi, there's an R. No. You're thinking immediately, okay, V equals I times R. You know that immediately. That's what I want you to be able to do with a transistor. With a transistor, I don't want you to see a transistor and say, okay, let's see, the hybrid pi model is this. That's what I see for the transistor. I want you to see its terminals and to see the resistances in those terminals immediately. To see the gain across those terminals immediately. See it by that symbol, not by a hybrid pi model. Okay, it looks daunting right now, but it really isn't. There's really just 6 equations. Here's equation number 1. And I won't actually write down the count because it may not end up being 6. But right, these are the equations we just derived. RB looking in this way into this generally loaded transistor. It is just little RE plus the big RE times beta plus 1, or R pi plus beta plus 1 times big RE. Right? It ends up being a bigger resistor. If I look up the emitter, I see a smaller resistor because everything gets divided by beta plus 1. And I've got two forms there that are exactly the same. So this is for R naught much greater than RC, which is generally the case for this class, but might not be for 140 in some cases. And so you may have to modify this a bit for some circuits. RC, looking down here, there's that equation I've written several times already, 1 plus all of this stuff here. These are all your familiar equations. And your gain equations. Gain from base to collector here, minus capital GM times R, and I've got a circle around that C. When I put a circle around the node, and that's the node, right? The node C, node B, node E. That means all that resistance in shunt with that node. Okay, so if I were looking at this, all the resistance in shunt with C is this big R, big C looking up that way, and this big R, little c looking down that way, in parallel. Okay? So I mean that total shunt resistance there. And then GM is just GM over 1 plus GMRE. We just derived that. For the case of emitter to collector gain, here to here, we just derived that. Same equation for gain, minus capital GM times R, all the resistance at node C going to ground. Okay, except now GM is this minus R pi over R pi plus RB times little gm. Okay, and then finally gain from base to emitter. Now it's basically this voltage divider here where RE is generally much less than Little RE is generally much less than big RE, so this is about equal to 1. I'm not writing that there for bipolar. You see a follower like this, if it's designed correctly, that's a gain of 1. And on the exam, you can calculate that gain and get 0.98, or you can just write 1. You choose. Okay? Then there's high-frequency analysis. We sort of did this, and I don't know if you recognize this. Don't worry, there aren't any really new equations for you here, right? So I don't count these. These are my 6 here. Those are the 6 equations right there. Okay? All right, there's another one right there. Sorry, there's 7. but the rest of this are not things you have to memorize. Okay, so for high-frequency analysis, what are you doing? You're just getting time constants. And the easiest way to do high-frequency analysis is just find all the capacitors that are shunt to ground. Because all you're looking for in high-frequency analysis is the time constant of the capacitor, of the resistance in parallel with that capacitance you're talking about. Okay, so in high-frequency analysis, I want to get all these time constants. I want to take 1 over all those time constants. But I'm going to identify my nodes. And I'm just going to say at node B, I've got that much capacitance in shunt. And that's just going to be all the resistance in shunt. Getting resistance in shunt is very easy to do. I hope you'll agree with me, especially after you've memorized those 3 equations of resistors. Okay, there may be 6 equations with gain, but there's only 3 resistor equations. Okay, and so tau B, tau C, tau E. This is just all the shunt capacitance with the resistance in shunt with that. The only one you cannot handle, or maybe this R mu naught, right? Which you know you can handle with Miller effect. Remember, with Miller effect, I can eliminate memorizing this with Miller effect. Now you have to know the Miller effect. But that to me is not memorization. That should be an innate thing that just comes naturally to you. It's like I'm out of time. And then this is the only extra equation you have to memorize. This resistor, because it's in feedback, see pi? Anything in feedback, beware this inspection analysis. I will say that again and again. But because that's in feedback, you do have to memorize this. I haven't derived this yet. I will in the next lecture. The rest of this thing is just those special cases that help you to apply all of this stuff. Okay? These special cases we just went through. Okay, next lecture we're going to do a multi-transistor example. I'm going to do it all with inspection analysis. Okay? So we're done today. See you Friday.
Right, this one is, you see this one is voltage divider, so you assume that there is no current coming from here?
Yeah, because R naught I said is big. If I say R naught is big. I didn't actually, let me do this here. Let me save this first.